Well, hello again, everyone. Today we're going to introduce sets and set class analysis. Take a look at this short little melody. It's 4 bars long. It's not going to win any awards. Let's just give it a listen. Nothing earth-shattering here. It seems not really tonal, but not really atonal in the traditional sense. We want to talk about ways it's held together. So to that end, I'm going to throw a few terms out here. A set is simply a collection of pitches, sometimes organized by pitch class. A set class is, think of it as a larger set that contains all sets of a certain characteristic, much in the same way that pitch and pitch class are related. A pitch is a very distinct point. A pitch class is all of those points on a keyboard or in the continuum. So C4 is a pitch. C is a pitch class. It contains all of the C's from C1 to C8. Thus it is with set class. The big word, segmentation. Segmentation is basically the process of dividing up something into constituent parts, bite-sized morsels, if you will, that we can work with. So let's take a look at this little melody and let's figure out how we can analyze it. Now, as we look at it, we see a very strong affinity with the first two measures. The second measure, first three measures all have the same rhythm. The first and second bars have a very similar contour at the beginning before shifting at the end. The third bar goes off a little different. Fourth bar is a completely different rhythm. But we can hear some affinities, so we might want to break it apart into these affinity zones and see what we can do. And this is where segmentation comes in handy. We would look at the first measure as a chunk. We would segment it out as its own idea. Same with the second bar, same with the third bar, and then by process of elimination, we'd probably look at the fourth bar. Again, this is a very simple introduction. When we get into class, we'll look at some greater challenges with regard to segmentation, but this one's pretty straightforward. You would probably not look at, say, this pitch here, and then this pitch, and this pitch, and this pitch, and pulled out a pitch from a different point in each measure. That wouldn't make any sense. You want your segmentation to be logical, and this would be an example of it right here, by measure. That makes a lot of sense. So let's take a look at this. Now, we see musically certain affinities. Major third, up a half step, down a minor third. Major third, down a whole step, up a minor third. It's an interesting little connection. Minor second, descending down a major third, up a major second. Up a minor second, up a major third, down a major second. We see some similarities, but not a whole lot. We get a sense, but we can drill down. We get a little further in there. So let's do some integer notation. An integer notation simply means you identify the pitch by number rather than pitch name. Assume C equals 0. Think of C being in the 12 o'clock position, and then move up by half steps. So C is 0, C sharp, D flat is 1, etc. So what we're looking at here is 7, 11, C is 0, A is 9. Start the next segment, 0, E is 4, E is 2, F is 5, E is 4, D sharp would be 3, B natural would be 11, C sharp would be 1, and then 7, 8, 0, 10. Now, sometimes in these you see 11 referred to as E and 10 referred to as T. That's just because when you have two numbers, a two-digit number, you have to be very careful. They're saying 2 ones in a row or 11. That will be more of an issue when we deal with 12-tone music. But this is the basics. This is the basic approach to segmentation. You can find intervals, find patterns, and sometimes we want to look at the numbers and see if they make sense. So if we're looking at each of these measures as its own segment, what we can then do is create different sets from these. So the first measure is its own set, and we usually define sets. Different books use different things. The text that we're using likes to do a certain way. I'm kind of trained. I'm kind of old and stuck in my ways. So for sets, not set classes or prime form or anything, just sets, I like to use parentheses and then the numbers with commas after each one. So that first set is 7, 11, 0, 9. Second set is 0, 4, 2, 5. Third set is 4, 3, 11, 1. And the last set is 7, 8, 0, 10. Up out of the way here so we can see where we're going with that. Now by itself, this doesn't tell us a whole lot. But if we rearrange these a little bit, maybe we can find some greater connections. So what we want to do is we want to put them in ascending order to start. We're not going to talk about normal order and things like that just yet. We're just going to see if digitally we can make some connections here. So let's rearrange 7, 11, 0, 9 into ascending order. So we'd start with, actually I guess we will be covering normal order a little bit. Normal order is simply the smallest possible rotation of the set. And by rotation, what we mean is reordering the pitches. So we start by putting them in ascending order starting on 0. So 0 is the smallest one, 7, 9, 11. And then we rotate that around, so we start with 7, 9, 11, 0. So these are the 4 possible rotations of this set. Now, once you have the 4 possible rotations, you want to say, okay, which one is the smallest from top to bottom? So in this case, 0 to 11, you're covering 11 half steps. That's an awful wide space. 7 to 0, you're covering how many half steps? Well, G up to C is a perfect fourth. That's 5 half steps. Remember, we're dealing with mod 12, so you can think of it this way. To get the distance for the first one, 11 minus 0 equals 11. In the case of the second one, 0 minus 7 equals 12 minus 7 equals 5. In the case of the third one, 7 minus 9 equals, under modulo 12, add 12 to the first number, 19 minus 9. That equals 10. And then 9 minus 11 equals 12 plus 9 is 21. Minus 11 also equals 10. So in this case, the smallest one, the smallest rotation, is this one. The second one here. And we say that this is normal order. And we would show that with square brackets, like so. We go through the same process for each of these. And I'll just go ahead and work them out here. We just 7, 9, 11, 0. For this next one, normal order actually would be 0, 2, 4, 5. Normal order for this one would be 11, 1, 3, 4. And, do the math. See why this works out. And the normal order for this last one is 7, 8, 10, 0. These are the smallest possible orderings. When you write them in ascending order and rotate them to find the smallest one, this would be the normal order for each of those. Now, you might notice a couple of patterns here. For example, 7, 9, 11, 0, 0, 4, 2, 5, 2, 4, 5. Let's take a look at these first two sets in normal order now. Well, what happens if say I were to compare the two. 7 to 9. How far up do I go to get from 7 to 9? 2 half steps. How far up do I go to get from 9 to 11? 2 half steps. How far do I get from 11 to 0, from B to C? Also 1 half step. So 2, 2, and 1 is what we call the interval schema here. Over here we have 0, 2, 4, 5. Well, 0 up to 2, 2 half steps. 2 up to 4, 2 half steps. 4 to 5, 1 half step. So in both cases, we see what we call an adjacency interval series of, sorry, I should have the brackets there, 2, 2, 1. That's kind of interesting. They share the exact same intervallic content. Different pitches, but they share the same intervallic content. Think about this for a second. Different pitches sharing the same intervallic content. This is kind of a big deal. Can you think of a tonal situation where you have two groups of pitches sharing the same intervallic content? Oh, I don't know. How about, this is going to script the formatting, but that's okay. Compared to two major triads, they have the same intervallic content even though they have different pitches. We can say that F is a transposition of C. And it's that idea of transposition that makes things interesting. Because basically what we can make an argument then is that this measure here is a transposition of this measure. Let's take a look at this third measure, 11 to 1. Well, go up 2 to get to from 11 to 1. Go up 2 to get from 1 to 3. Go up 1 to get from 3 to 4. This is also transposition. Even though the contour is different, these three measures are all related. Fourth one, if you look at it, you go up 1, up 2, up 2. That seems backwards. But it's the same numbers in the exact reverse order. It's kind of interesting too. We'll play around with that next time. I don't want to give away the whole ball game just yet, but we've got the beginnings of transposition and then something going on over here. We'll discuss this more in class. Meantime, if you have any questions, please ask them. I'm happy to answer them or at least try. And keep up your studies and have a great day.